carbohydrates. This is a class of chemicals that we're going to be discussing in great detail. You all have heard of this. You know from the diet world how carbs are sort of a critical part of our diet, and whether we should eat more carbs or less carbs or some carbs and not other carbs or complex carbs or simple carbs or whatever carbs, that is the debate that rages on, right? And let's try to understand maybe a little bit about these molecules, and then maybe we can make some decisions as to what's good for us without relying on, Instagram to tell us how we should eat. So, carbohydrate, carbon and hydrogen and oxygen. Hydrate essentially means water. So water is H2O, so it's made of hydrogen and oxygen and carbon. So that's the only atoms that are found in these molecules. Just those three atoms. They are called carbohydrates for that reason. They are sort of hydrated carbon, watery carbon. Now the water is broken up in pieces. The H's and the O's are not together, so that's fine. And we've already seen a good example of a carbohydrate, and that is glucose. Carbohydrates come in simple forms, which are called simple sugars. So the first group of carbohydrates are the simple sugars. Okay? And a good example of a simple sugar is our friend glucose. So we will draw glucose again. Because the more we draw glucose, the more we get used to drawing glucose. So we draw our little hexagon. Don't forget that oxygen goes in there. Oxygen right there in the corner. Then we will, I'm not going to do the shading of the Haworth projection. I'm just going to draw it like this because it saves some time, right? But we know that that's sort of a tabletop. I'll put my little sticks on here like this. Okay? And we know that this simple sugar, or this glucose molecule, comes in a couple of different forms. There's an HO here. I'll put the HO here and here. So you tell me what form it's going to be. Yeah, it's the alpha glucose, right? So there, and then this OH goes here, and this one goes here. Right, Andrew? I got them in the right spot, right? And our little CH2OH on the top. So the more you draw it, the more simple it becomes. So this is a simple sugar. It's called alpha glucose. And we know that there are other isomers of this already, but for our example, we'll just focus on one. Okay? Glucose has isomers. All of those isomers are also simple sugars. How do you define a simple sugar? Well, it's one ring. It's a molecule with one ring, and it basically exists by itself. And so glucose is a good example of a simple sugar. The other isomer of glucose that we could mention is fructose. Fructose is also a simple sugar because it's a single ring molecule. It's a pentagon shape. Okay? Yeah, I can go back. All right. So there are many simple sugars. We'll just use glucose for now as our example to get the concept. This glucose molecule is like a unit. It's like a Lego block. And it's possible to stick it together with another glucose molecule. So let's look at how that might take place. Let's draw our glucose molecule. We need more space here. Okay, let's draw our glucose molecule again, and we're going to have to draw two beside each other, so make sure you leave room for that. Okay, so I'll draw one here. Don't forget the O. I'll put the O in red. O. And I'll do my little lines here. I'll put my CH2OH up here. And we're going to start with alpha glucose, because it's the one that we're it's the simplest one that we're most familiar with, I guess. And put our OH up here, our HO down here. And there it is, alpha glucose. Now we're going to draw another one right beside it, over here. So this is good practice drawing glucose. Don't forget the O. I say that because when I first started teaching, I always forgot the O. When I'm drawing, I always just wanted to draw the hexagon, and then I'm like, oh crap, the O, every time. Oops, wrong color. Okay, that's a little weird. There we go. CH2OH up here. And this is going to be an HO down here and an OH on this side. Two alpha glucoses happily coming close to each other. All right, now what can happen? Well, you'll notice that in between them, there are two hydroxyl groups, two OH groups, which are functional groups, which means they can react with each other. They can interact, right? That's the whole point of learning functional groups, was that they can interact. And so what's going to happen is these two hydroxyl groups are going to link together. Let's continue. So look right here at these two groups, this one and this one. If they get close together, because they are functional groups, something can happen. What do you think? What kind of reaction do you think might occur here if you think back a couple of days? Yes, Kate? The one where you take the water out, the dehydration, right? Because we can see here that if I take this H and this OH and I remove them from the picture, if they get bumped off and a water molecule pops out, essentially H2O, then I'm left with this O right here and a big empty spot right here that wants to join. And what kind of a linkage would this be? Well, it's called an ether linkage, right? Remember? An ether linkage. When you have the linkage of just the O in the middle, that's an ether. So what we're going to see here, we're going to now draw the picture underneath of the two stuck together, and it's going to be super exciting. Okay, so here we go again. Draw our glucose. All right, so we have a glucose molecule here. Don't forget the O. And we'll put our lines in. Okay. Like that. CH2OH on top. An HO on the bottom. I'm not going to put anything on the right side yet. Leave the right side blank, because we have to see what it's going to look like when they join together. But the other ones we can put in. So we've got an OH here, an OH here. So we're just going to leave that right side blank for a second, and then we're going to go over here and draw the other glucose. Don't forget the O. There it is. We'll put our lines in. We'll put our CH2OH on top. We'll put our little OH here. We will not put anything on the left side because we have to wait and see how it joins. So leave that open. And then over here, we would have the OH down here. So what's going to happen in the middle? Well, if we go back a little bit, we remember that there was one oxygen atom that wasn't used, right? We took off two H's and an O, and we left one of the O's. So that O is still going to be here. And so we draw it like this. Like that. And we link them together. Okay, excellent. Now, this is what we call a two-sugar sugar. So it's got a name. If I go back up to, I'm going to go back up here to the simple sugars. Because it has one molecule only, we have a name for it. I'm going to write it up here. I'll write it in this nice purple color. It's called a monosaccharide with two C's. A monosaccharide means one sugar molecule. It's a monomer, right? It's a monomer that can form the building blocks of bigger molecules. So write that down. And then we'll go down to where we were before. Now we have something that's made of two sugars. So what do you think we'll call it? Not a poly, because poly means many. What means just two? disaccharide. So this is called a disaccharide. And this one has a very specific name as well. Okay? It's two glucoses stuck together. If you take two glucoses like this and you stick them together, you get a molecule that has a name. He's called, I'll put him in a different color, he's called maltose, or what we sometimes call malt sugar. Remember, all the sugar molecules have the O's ending. Fructose, glucose, maltose, right? But maltose is an example of a disaccharide. So there are many disaccharides, because you could imagine, we put two alpha glucoses together. We could put an alpha and a beta together, or we could put a galactose and a glucose together and get all kinds of options. All right, we could put all these different molecules together, and those would be all disaccharides. Question? Oh, okay. Good question. You're asking me if we were writing this as a chemical equation, right? That water would be part of the equation as one of the products of the reaction, and you would write it. But we're not actually drawing chemical equations. We're just drawing pictures of what things happen, what they do. So all we have to know is that this is a dehydration reaction, okay, that happens between these two simple sugars. So a good thing to write as a sentence might be, maltose is formed by the dehydration of two alpha glucose molecules, right? Or you might use condensation if you like the old style better, but dehydration is probably better because that's what everybody says nowadays. So you could write a sentence like that. Maltose is formed by the dehydration of two alpha glucose molecules. Now I want to say a couple of extra things about this. I want to say a few things about this picture, part of the picture right here. It's important to remember that the two OHs that joined, and I'll go back up to show you that, were on the same side. They were both down OHs. You see that? They were both down. If you had a molecule on the right side who had an up OH on that side, it would form a slightly different kind of link. It's the same bond with an oxygen. It's still a dehydration. Everything is the same, but the shape of it would be different. So I'm going to pause again and do some demonstrations to show you how that would work. Okay, so in this green circle, we have a grabbing of the two molecules together on the same side. And it's called an alpha linkage, because you're linking the OHs on the same side. And it makes sense to call it an alpha linkage because we used alpha glucose, right? Now it's possible that the right-hand molecule could be a different isomer, and the OH could be up instead of down, and you'd get a cross grab. So let's draw a picture that shows us the cross grab, which is a slightly different shape. So again, we will draw our glucose molecule. By now, you probably have it memorized. Okay? Don't forget the O. If I don't say that every time, I'm likely to forget the O. That's why I do it. It's not for you, it's for me. I'm telling myself not to forget the O. Okay. All right. So this will be an alpha glucose on this side. Okay? And well, what the heck? Let's draw them separately first. Why not? We'll practice our drawing. And then we have our CH2OH up here. And we have our OH here and our OH down here. Okay, so there's one. Now what we're going to do is we're going to draw, let's see. Actually, I've changed my mind. I just looked at the textbook. I like their example better. I was going to go do a certain molecule because later we're going to learn about cellulose. But I just thought this one might be more fun because there's a cool biological sort of thing about it. So I'm going to erase this. And I'm going to flip this. Okay? I'm going to flip it to our friend who's like this. So who's that? That's beta glucose. So we're going to start with beta glucose, right? And I'm going to write that underneath just in case when you're looking at it later, it's so easy to miss that. I'll put beta glucose there to remind us that this is a different isomer of glucose. And then on the other side, we're going to put just a regular alpha glucose on the other side. So watch this. Here we go. Make our hexagon. Didn't leave enough room there for the O. Forget the O. There we go. Like that. Oh, it's supposed to be black. Rats. Okay. Thickness. Got it. Black. Okay. Smart board. Not too smart. They say computers are only as smart as the people who use them. I refuse to accept that. I believe that this smartboard actually is making decisions to thwart me on purpose. It's not my fault. Okay, so here we have them. You see I put the OH on the bottom. Okay, so now when these two get together and there's a dehydration reaction, there's going to have to be a holding hands that's going to have to be across instead of on the same side. All right, let's go and do the dehydration of this. So we have to draw two more glucose molecules. Well, actually, a beta glucose and an alpha glucose. So let's draw. Here we go. Here is the beta glucose. Leave room for the O. Here we go. And what we're going to do is draw this line here, but not label it because we have to put the linkage in there. So we'll just do the rest of the molecule first. CH2OH over here, the HO down here. That's that. This has an OH here, and this has an OH here. And then we will draw the other one over on this side, like this. Left room for the O. Right there. And then we'll draw this here like this. We'll put our CH2OH here. And we'll put the OH here, the OH here, and of course the OH over here, because this one is an alpha glucose. So now look at the way our linkage works. It goes from this top to this bottom, and in the middle is the oxygen. So instead of being same side, it's a cross-arm kind of joint. And we call this a beta linkage, which means that it's linked cross instead of on the same side. So as a visual, you can imagine holding hands with someone who's facing you. If you both hold hands on the same side, that would be one right and one left. That's the alpha linkage. But if you cross your arm across your body so that both of your right hands are grabbing, that's the beta linkage. Question? Say that again? Yeah, it's a cross-type linkage, right? So it's not really called a cross linkage. Well, maybe you could, I guess. It's called a beta linkage. And the thing to remember is that these two linkages cause a slightly different shape. This molecule looks very much like maltose, but it is not maltose because it behaves differently chemically because of the different linkage. Its name is, it's also a disaccharide though, right? It is a disaccharide, but its name is lactose. And that's why I thought we would do this one, because there are some people who are lactose intolerant. Right? And so we can actually now understand why they are lactose intolerant. So in your body, we're going to learn later about how enzymes work, but enzymes are little protein molecules that help reactions happen. So for every reaction in your body to happen, you pretty much need an enzyme whose job it is to make it happen. So you have millions of enzymes. And there's an enzyme for causing this maltose molecule to break apart. It can put this molecule in such a way that it puts just enough stress on this alpha linkage that it will pop apart, and we can digest this molecule. We can break it back up into its two glucose monomers. which can then be used, just hang on for the question, which can then be used in your bloodstream for energy. And that's because the shape of the alpha linkage has this enzyme, right? Or there's an enzyme that works on that shape. Now here's the cool thing. That enzyme will not break the lactose because it's a different shape. To break the lactose, you need a different enzyme to break this into its two monomers, which can then be used for energy. Here's the cool thing. Enzymes are made by your genes. And if your genes lack the instructions for making the lactose breaking enzyme, then when you eat lactose, your body will not be able to break this linkage apart. And so lactose intolerance means that your DNA does not have a code to make the enzyme to break this molecule apart. So when you eat it, it just stays this way in your stomach and goes into your intestines. Now, there's other things that live in your intestines. Bacteria that live in your intestines have different chemistry. They have their own enzymes and they can break this apart no problem. So what you've essentially done when you eat lactose is you've filled your intestines with super bacteria food, which means they go nuts and they break it down like crazy. In the process of breaking it down, they produce byproducts like gas. And the gas fills up your intestines and makes you feel crappy. You get the bloated, gassy, distended feeling that you get when you're lactose intolerant. But another person who has the genes to make this enzyme, well, his bacteria or her bacteria aren't getting this lactose in the intestine. It's already broken down into its monomers, and so there's less problem with gases and building up. And so lactose intolerance is because of the alpha and beta linkage that can happen between two glucose molecules. An alpha and an alpha, everybody can digest that. But an alpha and a beta, only some people can digest that. All right, so to sum up, we have disaccharides, which are made of two sugar monomers, which can be anything, but we chose one example, right? And of course, there are different kinds of linkages that can happen between them, which produce different molecules in different shapes. And so we have seen that there's the same side linkage. The same side linkage is called the alpha linkage, and the cross side or opposite side linkage is called the beta linkage. And what's important, whoops, I made an alpha. It's important because the beta and alpha linkage produce different shapes, and of course, shape is everything. And so that means that you get two completely different molecules that act differently. And the example we had was an alpha glucose plus another alpha glucose, and it produces an alpha linkage between the two, and that was called the sugar maltose. Whoops, that's an A there, M-A-L, maltose. But if you take a beta glucose and you stick it to an alpha glucose, we saw it's possible to get the beta linkage or the cross linkage. And that is basically, it's the same two sort of molecules, but because of the isomers, not sure what happened there. Continue. I don't know what's happening. I'll have to figure. All right, we fixed that problem. Sorry about that. So we had the beta and the alpha creating the beta linkage, which is a whole different shape. And that different shape means it reacts differently chemically, and it has a whole different name, and it was lactose. So isomers getting together in different ways form different kinds of links. So the disaccharides are two sugar units linked together, and they can either link with a beta or an alpha linkage, depending on which isomers you're putting together.